and welcome back to the course of Basic Electrical Engineering. In this video lecture, I am going to continue with the Unit 2, that is AC circuit. The topic that I am going to discuss in this video lecture is analysis of series RLC circuit. In the previous video lecture of AC circuit, I have already discussed about analysis of series RL and analysis of series RC circuit. So let us start with the series circuit, which consists of resistor, capacitor and inductor. So here you can see one resistor, one pure inductor and one pure capacitors are connected in series. The resistor is having value R ohm, inductive coil of inductance L and capacitor of capacitance C farads are connected in series. Now, across this series combination, one instantaneous voltage source is applied, that is represented by Vm sin omega t. One AC source is connected across the series combination of these three elements. Now, as current will start to flow because of the voltage source, there will be potential difference across every element. So let us define VR as a potential difference across R, that is given by I into R. VL is a potential difference across L, that is given by I into XL, and VC is a potential difference across C, that is given by I into X. And F is a supply frequency. Here omega is there, so omega is equal to 2 pi F, where F is a supply frequency. Now, all these three elements are connected in series. Same current will flow through all these elements, and as same current is flowing, we know we have to take some reference quantity whenever we are drawing the phasor diagram. So here we are having total 4 quantities: I, VR, VL, VC. So current will be taken in this case as a reference phasor because it is common to all three elements. So let us discuss about the phasor diagram of RLC series circuit. Now, as circuit consists of three elements which are connected in series, so current, as I told you, will be taken as a reference whenever we are drawing the phasor diagram. So current is represented by straight line. Phasor is nothing but the representation of alternating quantity. We have already discussed, which makes the representation very easy. So this is a current I which is taken as a reference, which is passing through origin. Now VR is a voltage difference across R. Now we know for resistor, voltage and current are in phase. So VR is in phase with the I. So VR will be in same direction as that of I, and phase difference between them is 0. Next quantity is a VL. Now we know for purely inductive circuit, VL, that is a voltage difference across, potential difference across the inductor. VL leads the current by 90 degree. So VL, current is taken in this direction, so VL will be in upward direction. It will be not in downward direction because we assume that phasors are rotating in anti-clockwise direction. As VL is leading the current by 90 degree, so it will be in this direction because phasors are always drawn in anti-clockwise direction. So VL leads I by 90 degree. Third one is a VC, which is a potential difference across the capacitor. And we know for purely capacitive circuit, current leads the voltage by 90 degree, or we can say voltage lag behind the current by 90 degree. So as phasors are drawn in anti-clockwise direction, so VC will be in downward direction. So we can say this angle is 90 degree. If we travel in anti-clockwise direction, we can see I is leading VC by 90 degree. I is lagging VL by 90 degree. So this is how we can draw the phasor diagram for series RLC circuit. Now, VL and VC are exactly in opposite direction. They are in phase opposition, and phase difference between VL and VC is 180 degree. So they will try to cancel out each other. So as VL and VC are there, there will be three possibilities, and I am going to discuss two possibilities in this video lecture. That is, first one is a VL greater than VC, second one is a VL less than VC, and third one is a VL is equal to VC, that I am going to discuss in the next video lecture and in the video lecture of resonance. Now, as VL will be greater than VC, So phasor diagram will be different. If VL will be less than VC, phasor diagram will be different. So let us take one by one. So let us first take VL greater than VC. In this particular case, what will the behavior of the circuit that I am going to discuss. So again drawing the same diagram. Now as VL is greater than VC, so resultant and VL and VC are in phase opposition. So resultant vector both will try to cancel out each other. So resultant vector will be in the direction of VL because VL is greater than VC, and that resultant phasor will be VL minus VC because both are in opposite direction. So this will be in this direction. Now VR is in phase with I. Now taking the projection of VL minus VC over here. So this becomes the voltage triangular that we have already discussed in the previous video lecture. Why it is known as a voltage triangular? Because all the sides are voltage. And this is the resultant voltage of the circuit, that is a phasor sum of VR and VL minus VC. Now, as VL is greater than VC, what will the behavior of the circuit? Because circuit consists of resistive element, inductor and capacitor. So, as VL is dominating over here, so circuit behavior will be inductive. So, circuit will behave as an inductive circuit. Now, from this phasor diagram, we can find out the angle phi, or we can find out the resultant voltage. So resultant voltage is a phasor sum of VR and VL minus VC. So VR is equal to, if we take the magnitude of that, V is equal to square root of VR square plus VL minus VC whole square. Now we know the value of VR, VL and VC. Putting those value, so V is equal to square root of IR whole square plus IXL minus IXC whole square. Here VL is greater than VC, so it will be IXL minus IXC. Now taking I common, so V is equal to I square root of R square plus XL minus XC whole square. So finally I is equal to, that is the current of the circuit, V divided by square root of R square plus XL minus XC whole square, where we know I is equal to V divided by Z. So this denominator term becomes the impedance of the circuit. So where square root of R square plus XL minus XC whole square is equal to impedance of the circuit, that is denoted by Z. So I is equal to V by Z. Now finding out the phase angle of this circuit. So for this particular diagram, now we can see tan phi is equal to VL minus VC divided by VR. Now putting the value of VL minus VC, that is I into XL minus XC, and VR is equal to IR. So I gets cancelled out from numerator and denominator. So XL minus XC divided by I, that is a tan phi. So we can find out the phase angle from this voltage triangular. So phi is equal to tan inverse XL minus XC divided by R. And V is equal to square root of VR square plus VL minus VC whole square. So when VL is greater than VC, resultant current is lagging behind the voltage by some angle phi, because this is an inductive circuit. So final expression of current becomes I is equal to Im sin omega t minus phi when VL is greater than VC. So now what about the power consumed in this circuit? As this circuit is behaving as a series RL circuit, because VL is greater than VC, so power consumed in this case is equal to series RL circuit average power. So P average is equal to VI cos phi, and that is the power consumed by resistive element. Now impedance triangular for VL greater than VC case. So drawing the voltage triangular, that is VR is equal to I into R, VL minus VC is equal to I XL minus XC, and V is equal to I into Z. Now this is a voltage triangular. If we divide all the sides of the voltage triangular by current I, we can get the impedance triangular. Why it is impedance triangular? Because one branch consists of R, and other branch consists of reactance and impedance. So impedance triangular shows the relationship between R, Z and X. Now from this impedance triangular, we can also determine the power factor, that is cos phi is equal to R divided by Z. Now power triangular. So to draw the power triangular, we should have first the voltage triangle. So again drawing the voltage triangular. Now if we multiply all the sides of the voltage triangular by current, we will be getting power. So this triangular consists of power. All the sides are power. Now this is nothing but the apparent power we have already discussed in the previous video lecture, because it is V into I. V is the total voltage and I is the total current. So this becomes the apparent power. Now this is the reactive power, imaginary power. So Vi sin phi, because this component, this component is nothing but the V sin phi. This side is nothing but the V sin phi. If we multiply these sides by I, we are getting Vi sin phi. And this, if we multiply these sides by I, we will getting I square R. Now this side is the active component of V, so Vi cos phi into I. So I square R is equal to Vi cos phi. That is the active power, true power or real power consumed in this circuit. So this is how we can draw the impedance triangular and voltage triangular, power triangular from the voltage triangular for series RLC circuit. Now moving towards the next case, that is VL less than VC. If VL less than is VC, so our phasor diagram will be looking like this way, because VC is dominating over here. So resultant vector of VL and VC will be in downward direction. So this is VC minus VL, taking the projection over here. So this becomes the voltage triangular, and this is nothing but the resultant voltage of the circuit, which is phasor sum of VR and VC minus VL. Now the circuit behaves as a capacitive circuit, a series RC circuit, because VC is dominating over here. Now from this phasor diagram, what we can determine? We can determine the resultant voltage. So V is equal to square root of VR square plus VC minus VL whole square. Now putting the value of VR, VC and VL, we are getting V is equal to square root of IR square plus IXC minus IXL whole square. Now taking I common from the square root. So V is equal to I in bracket R square plus XC minus XL whole square. In the previous case, here we are having XL minus XC. Here it is XC minus XL, because VL is less than VC. Now I is equal to V divided by square root of R square plus XC minus XL whole square. Now we know I is equal to V divided by Z. So this term is nothing but the impedance of the circuit. So we are defining this as the impedance of the circuit, and it is denoted by capital Z. So I is equal to V divided by Z. Now phase angle. From this circuit we can also, from this phasor diagram we can also determine the phase angle of the circuit. So tan phi is equal to VC minus VL divided by VR. And putting the value of VC minus VL in terms of I and X, so it will be IXC minus XL divided by I into R. VR is nothing but the IR. Now I gets cancelled out from numerator and denominator. So final tan phi is equal to XC minus XL divided by R. So phi is equal to tan inverse XC minus XL divided by R. And resultant voltage V is equal to square root of VR square plus VC minus VL whole square. Now as VL is less than VC, and from this phasor diagram we can also see resultant voltage lags behind the current, or we can say resultant current leads the total voltage by some angle phi, because the circuit is now behaving as a capacitive circuit for VL less than VC. So now we can write the expression for current using the phase angle expression. So I is equal to Im sin omega t plus phi. Here it is a plus sign because it is a capacitive circuit. Circuit is behaving as a capacitive circuit, and current leads the voltage by some angle phi. So final expression of current is I is equal to Im sin omega t plus phi. Now, as the circuit is behaving as a RC circuit, power consumed in this circuit is equal to series RC circuit power. So P average is equal to VI cos phi. Now moving towards impedance triangular and power triangular for VL less than VC. So to draw the impedance triangular, we should have voltage triangular first. This is a voltage triangular for VL less than VC case. Here it is I into R. Here it is VC minus VL, which can be expressed in terms of I into XL, XC minus XL. And here it is V is equal to I into Z. Now if we divide all the sides of voltage triangular by current, we will be getting the impedance triangular. So impedance triangular consists of, impedance triangular shows the relationship between R, Z and XC minus XL, that is capacitive reactance or net reactance X. Now from this impedance triangular we can also determine the power factor of the circuit, that is cos phi is equal to R divided by Z. But here Z is square root of R square plus XC minus XL whole square. Now next one is a power triangular. So to draw the power triangle, we should have voltage triangular. Now again drawing the voltage triangle. Now all the sides of voltage triangle consist of voltage, even, and we know if voltage is multiplied by the current, we'll be getting the power. So if we multiply all the sides by current, we'll be getting the power. Now VR, we can write VR is equal to V cos phi over here. This is active component of the resultant voltage, and here we can write VC minus VL is equal to V cos sin phi. So if we multiply this branch by I, this side by I, will be getting I square R is equal to VI cos phi. Here we'll be getting VI sin phi, where VI sin phi is a reactive part of the V, and this becomes V into I. So we know this V into I is nothing but the apparent power. VI cos phi is the actual power consumed in the circuit, and VI sin phi is a reactive power, useless power. And we know actual power consumed in the circuit is because of resistor, so it can be also expressed in terms of I square R. So this is all about the today's video lecture. In this video lecture, I have discussed series RLC circuit, and for series RLC circuit, I have discussed two cases: VL greater than VC and VL less than VC. Hope you have enjoyed the video. See you soon in the next video of the AC circuit. Thank you for watching.